Hello, everybody. Thank you for attending to the presentations. I'm Mateo Guaita, and I'm in the beginning of my second year. And my thesis is on the modeling of plasma thruster plumes, and in particular, their kinetic aspects. So first question is, why are we interested in plasma plumes? The first and main reason is because the plasma inside of the plume can interact with the spacecraft, causing damage by erosion or by electrostatic charging. In some cases, such as magnetic nodules that we've seen a lot of today, what happens in the plume can also influence the performance of the thruster. And then there are also more futuristic, let's say, ideas which have been proposed in the space community. What models are available? The first and quickest ones are fluid models, like the ones that Diego presented, which are very fast, so we like them for this. But at the same time, they do present some problems on the modeling of electrons. In particular, we need to find a way to close the fluid equations and make assumptions on the VDFs. Peak models, such as the ones that Enrique presented, instead use basically the plasma species are modeled as particles which bounce around, and they are very accurate, but they are also computationally very expensive. A compromise between these two are hybrid models. They use the particle approach for the heavier species and the fluid approach for electrons, which means that they maintain the inaccuracies linked to the electrons of the fluid model. But on the other hand, they are computationally affordable. And finally, we have kinetic models. These models solve the Vlasov equations, which means that if we want to solve or approach the model the problem in its full dimensionality, they become extremely computationally expensive. If we make some heavy simplifications, they can even give analytical results. So they can be good for a first approach to the problem. Now, what are the main challenges in a simulation of a plume? Well, the main challenges are linked to electrons, basically. Why? Because the thermodynamics of electrons and their potential are what define the electric forces inside of the plume, which then influence the trajectories of all of the particles. However, the electrons can be very complex to model. In particular, to correctly capture their distribution function, we need to simulate the transient of the setup, we need to impose proper boundary conditions, and all of this leads to computationally expensive codes. So what we want to try to do in the framework of my thesis is find a computationally affordable approach to the electron modeling in particular, and then hopefully use this to then derive some fluid closures which are quick enough and accurate enough to be able to use them in fluid models. So what is the modeling strategy that we propose? Well, using a full peak approach would be very nice, but it's too computationally demanding. So what we propose to do is a formulation which we have termed coffee, which mixes the two worlds. So we will have a fluid population of electrons, which is responsible for reducing the computational costs, and a kinetic, so a particle population of electrons, which is instead responsible for giving us the nice kinetic and accurate responses that we want. So let's go through the code very quickly. The heavy species are modeled as particles, as is traditional for hybrid codes. And then we have the fluid electrons, which are the majority of the electrons in the simulation, and they are responsible for giving us very efficiently the potential inside of the plume. On the other hand, we have the kinetic electrons. These electrons are particles, they are a much smaller fraction, and they are responsible for giving us the kinetic information of the electron population, which can then be fed back to the fluid electrons. So let's take a look at some results. So this is just a simulation setup. It's a very simple planar and 2D plume in which there are no collisions, no magnetic fields. It's just xenon ions and fluid and kinetic electrons. And the kinetic electrons inside of the plume, the fluid electrons, so the fluid equations are closed with a simple polytropic. So if you're not familiar with the polytropic closure, it just states that the temperature of the fluid electrons is dependent only on the fluid electron density. And we close this with a polytropic parameter, which is gamma, which is a free parameter of the model, so we can choose it. And we can, let's say, search for a value of gamma that makes it so that the fluid temperature along the plume axis matches well with the kinetic electron temperature, which is the red line. Now, along the axis, we have a very nice result. It matches very well. Instead, in the lateral directions, the ideal value of gamma, which in this case is 1.09, let's say it matches well at the center. At the sides, it decays a little bit, but we will see this further. So what effect does this have on our two populations of electrons? Well, here you see the ion density map, which, since we're assuming quasi-neutrality, is equal to the total electron density map. And here you see the fraction of kinetic electrons with respect to the total electron density in the plume. This fraction, nominally, we inject 10% of kinetic electrons. So if this was exactly 10% all over the plume, we would have a perfect matching between the fluid model and the kinetic model. It's not. It's close. It's not too far. We go from 9%, well, from 10% injection to 7% at the edges of the plume, but it's not the same. What this means is the two models are close enough, but they're not identical, which is what we're expecting. And now the question is, why are they not identical? And the reason is mainly to be looked for in the electron temperature. So here we have at the top left-hand side the fluid electron temperature inside of the plume. And in the polytropic and fluid approach, the fluid temperature is a scalar. In reality, in the more general sense, we know that temperature should be a tensor. So for the kinetic electrons are capable of giving us all of the components of the temperature tensor. And we have that what we were matching before was the scalar fluid temperature with the average of the diagonal components of the kinetic electron temperature. And these two match quite well. However, what this is hiding behind it is that these are the two components along the diagonal of the kinetic electron temperature, which do not match at all with the fluid temperature. So the reason why we are having a discrepancy between the fluid formulation and the kinetic formulation is behind the fact mainly, not only, but mainly behind the fact that the fluid is not properly capturing the anisotropy in the temperature tensor that instead we see with the kinetic population. So how can we make this better, or at least what are the limitations we're finding for the polytropic closure? Well, let's start from the, let's say, from the scalar value of the temperature. So if we are trying to match the scalar fluid temperature with the average of the components of the temperature tensor from the kinetic electrons, we have that gamma would not be, if we want them to match identically, gamma cannot be a single value, but we would need a local value, which varies from 1.1 to 1.2 roughly in the simulation. So already one single value of gamma in the polytropic closure is not enough. If then we want to say, okay, but temperature is a tensor and I want to be able to compute all of its components with some kind of polytropic closure, then now we need at least two values of the polytropic coefficient, one for the XX term of the tensor, one for the ZZ term of the tensor. And once again, they're not a single value, but they need to be, they have to have a local value spread throughout the domain. So this means that now finding a polytropic closure becomes extremely complex because we can't impose a single coefficient. We need to impose maps of at least two coefficients to match the temperature properly. So this was just an overview of what I've been doing in the last year mainly, which is the analysis of the polytropic closure. I've also been doing some side jobs, let's say, which are the inclusion of collisions in the model. So now kinetic electrons are capable of colliding with neutrals and with themselves and with ions as well. Also, I've been verifying the model with Achilles, which is one of those simple kinetic models which I was mentioning before, which is semi-analytical. These are just some quick results of the distribution functions, which match quite well. And instead, going forward, the plan is to try to implement, to try to capture the temperature components of the tensor with a polytropic closure with three coefficients, one for each direction space. Then pass to the quasi-neutral full peak formulation, so dropping the fluid population, but trying to maintain the computational advantages that it provided, include mildly magnetized cases, improve the collision library that we have at the moment, and finally try to validate the model with experimental data. So these are the contributions, which are 2 workshops and a lot of technical notes for the project, which I'm funded by, which is a commodities led by ISA. And that's it. So if I have any questions.